Check out this sweet neuron that was made by a student in another class. Look at that thing. Awesome. Nice job, Peter K., who made this incredible model. Wow. Dendrites over here, soma, axon, terminal buds down here, I guess. All right, so this is the action potential video, and the first part of the video is going to just look at a particular spot in the membrane, and the second part of the video is going to look at how the signal travels or propagates down the length of the axon. All right, enjoy. Welcome to the membrane of a neuron, phospholipid bilayer. This is the inside of the cytoplasmic side. Here on this side would be the outside, and these are the materials we're going to use today. So these little green plastic things, they'll represent potassium. Yellow will represent sodium. Little circular copper-looking things, chloride. Random shapes, proteins. And these things will be ligand. So we're going to set up resting membrane potential first, so you can see how the different concentrations of these things affect the charge across the membrane. Let's start off with the chloride ions. So, majority of the chloride ions are sprinkled on the outside of the cell. There are some chloride ions on the inside, but most of them are on the outside. These big proteins, different types, are on the inside, and they are negatively charged too, and they influence the membrane potential just by being there. Most of the sodium ions are going to be on the outside, patiently waiting for their opportunity to go inside. And there are some sodium ions on the inside, but most are on the outside. Conversely, most of the potassium ions are on the inside. Potassium on the inside, but there are some on the outside as well. But most of the potassium are on the inside. Okay, so this is called resting membrane potential. And there are a bunch of things that contribute to this. The leak channels, potassium leak channels are always leaking, so potassium can always go through those. The sodium leak channels are always open too, so they are always leaking. Sodium can go back and forth between those. The voltage-gated sodium channel is shut in this case. The ligand-gated sodium channel is shut, and the ligand-gated is shut here. And then the two potassium voltage-gated channels are also shut. Constantly working in the background here is the sodium-potassium pump. It's an ATP-driven pump, which is going to move 3 sodiums out for every 2 potassium in. So I just moved 3 sodium out and 2 potassium in, and that's going to be working in the background all the time. Let's start now. All right, so resting membrane potential is right here, say negative 70 millivolts. But let's say we get to a stimulus right now. In this case, it will be a neurotransmitter, which is attaching. So a ligand is attaching to a receptor, and that's going to cause this little doorway to open. That increases the permeability of the membrane to sodium. So a little bit of sodium just came in. But maybe a little bit of sodium came in. So that might cause the charge to go up a little bit here. But that's not a strong enough stimulus for a threshold. So maybe the neurotransmitter is degraded, and there isn't any around anymore. And so it goes back to resting for the reasons listed earlier. So we're back to resting. But let's start over again here and try again. So let's have a little bit stronger stimulus. So let's bring in 2 neurotransmitter molecules right here and here. That's going to pop open both of these doors. So that means the permeability to sodium is even higher than before. So more sodium can come in. And it won't be long until we reach threshold potential. At threshold, the voltage-gated sodium channel opens. And now we have the maximum permeability to sodium, so the most permeability for this. So we have sodium coming in here, and over here through these, and so on. And that's going to cause this to rapidly rise to this point here. Now, at that point, what will happen is that these little doors will shut here and here and here. They're going to close on the inside, these doors. And these aren't actually shut yet, but that's okay. It is shut to sodium. But now we're going to open up the potassium channels. So the voltage-gated potassium channels here and here, they're going to pop open, and potassium is going to rush out. So here's some potassium rushing out, potassium rushing out, some potassium rushing out. Now, once we get back to resting, these potassium doors are going to close, but they're slow. Watch this. Slow. Ooh, I snuck out. Ooh, I snuck out. Ooh, I snuck out. Hey, here's another one. Ooh, I got through. Yeah, almost. Yep. And OK. So all of that sneaking out, because the doors are closing slowly, that period of time, it gets you down right here. And now we're back to the same conditions that would lead to resting membrane potential. So the leaking potassiums are leaking. The sodium leaks are leaking. These doors would be shutting at this point. These could then open at that point. All right. And the pump is pumping. So the pump will move 3 sodium out for every 2 potassium in, ATP, active transport against a gradient. And that's going to help maintain a nice gradient across that membrane. And that will bring you back to resting membrane potential, and you can do it again. What you learned in the first half of this video is how an action potential operates within one small section of a neuronal membrane. It's kind of like running in place on a treadmill. But how does it propagate? How does it get traction and actually travel a linear distance? So how would it then move on over here? Well, that's what we're going to look at right now. So let's jump through this a little bit more quickly this time. So here's ligand binding to receptor, ligand binding to receptor, opening up both of those sodium channels. So sodium can rush in. Oops, sorry. So sodium can rush in, and that gets us to threshold. Now at threshold potential, the voltage-gated sodium channel nearby will open. And that increases the permeability to sodium. So sodium's coming in, sodium's coming in, and sodium's coming in. So we'll fast forward that. Sodium all came into the thing. Good. So we'll close this up from this end, close this up from this end, close this up from that end. So the extra sodium that has rushed in, let's watch to see where it goes. So it's diffusing laterally. And guess what? You've been depolarized, which means that the membrane potential here just reached threshold because of the sodiums that were delivered laterally on the interior and the cytoplasmic side. So these doors are all voltage gated, okay? Not ligand gated, but voltage gated. And so now we do this kind of thing again, sodium rushing in, sodium rushing in, sodium rushing in, and that gets us to this point. And then this would play out. Now meanwhile, back in the first game board, way over here, this one has to finish off the whole story. So we are at the overshoot, and that's when the potassium channels, voltage-gated potassium's open, so potassium rushes out. That brings us towards repolarization. Potassium rushes out. And maybe that brings us all the way down here to the resting membrane potential. At that point, all of our sodium channels are fully closed. All right, good. And our potassium channels start to close as well. So closing slowly, closing slowly, closing slowly, closing slowly. And that brought us to this point here. And then through the combination of potassium leak, sodium leak channels, and the sodium-potassium pump, ready? 3 sodium out, 2 potassium back in. That combination of factors brings us back to resting membrane potential. And then back to the other game board that was also happening. And that's how it travels down the length of the classroom, which in this case is only 2 tables long. But imagine it was hundreds of tables.